Our next notion has to do with something called standard position. An angle can be expressed or can be drawn in what is called standard position. It turns out that everything that we use standard position for in trigonometry, we could, in the strictest sense, get by without it, but it makes so many things so much more easy and so much more straightforward. The standard position, what eventually happens is you start to put things in standard position almost without even realizing it. Many of the pictures I've drawn already, you don't know this yet, but many of the pictures I've drawn already have been in standard position because it's just such a natural thing to do. But this makes it official, and this makes this gives us the rigorous definition of what actually is supposed to be occurring, and we'll take it from there. So, an angle. Remember what an angle is. Remember we have a ray, and initially the ray can be in any direction, starting anywhere we want. And then we take another ray and rotate it. It has to have a common endpoint, and so it must rotate it. Remember, if you rotate counterclockwise, that's positive. Rotate clockwise, that's negative. So we can think of it doing like this, right? We have this, here's my ray, and if we rotate it, then that's what we're talking about with an angle. So we rotate it however many degrees we want to, or we may, if we wish, rotate in the negative direction, all right? And there's nothing in that definition that makes any specification as to where this ray might be located. You could, if you want to, start with a ray down here. And now we're using that as the initial side, and now there's the terminal side, and there's my angle. And so we are free, as far as the definition of an angle is concerned, to put this initial side of the ray in any position we like, any location in the plane. However, it turns out that it becomes significantly, and not just, this is not a small gain, this is a huge gain in ease and convenience and notation, to do the following. An angle is in standard position. An angle is in standard position if it has it meets these two requirements. Number one, the vertex is at the origin. And when I say that, I mean this. Consider the XY coordinate axis. What we're going to do is slap an angle. We're going to slap a coordinate system in the plane that contains the angle we're dealing with. Requirement number one to be in standard position is the vertex must be at the origin. And so if I have an angle right here, and I think of rotating this angle through this, there's my angle. This angle is not in standard position because the vertex, right, the common endpoint of the two rays, the vertex is not at the origin. If I start with this and I rotate in this direction, that angle is wonderful, but it's not in standard position. All right? What must happen, we can do this. Suppose I have this angle and rotate it here. This angle is not in standard position because the vertex is not at the origin. All right? So what is required is the vertex must lie at the origin. So here's an angle. So far, so good. But there's one other requirement. There are two things that must be true. Both of these must be true. So both of these must be true. The initial side must be on the positive x-axis. The initial side must be on the positive x-axis. If I'm going to take an angle and form it by rotating, this is the initial side, the one that stays fixed. That must be on the positive x-axis, and that point, that vertex, must be at the origin. And what that means is, in order to be in a standard position, this angle must be of this variety. There, I've just taken that angle. See what I've done? Initial side is on the positive x-axis. Vertex is at the origin. If I draw the picture, then I have there's my angle. That is in standard position. And so what then we can say is we can draw all sorts of angles in standard position. Initial side, terminal side. or we can draw an angle in standard position. Initial side, terminal side. Remember, if we want to regard this as a positive angle, now we're talking about that. Remember the word reflex angle, greater than 180? If we're talking about the negative measure, then we can talk about this angle. This is the negative measure, this is the positive measure. But this is in standard position. Suppose I have, this is the initial side, this is the terminal side. I have an angle whose measure is 90, and so that angle is in standard position. You can have a straight angle. A straight angle, there's the initial side, there's the terminal side. That angle's measure is 180 degrees. That angle is in standard position. Angles in standard position. All right. All right. Now we incorporate the advantage of having the coordinate system. The language becomes convenient and useful. And so we have angles in quadrants. Remember, if this is the coordinate system, this is quadrant 1. Remember when you did this in basic algebra and you wondered, why do they why do they number them in this weird sort of, here's 1, here's 2. Why don't they just do 1, 2, 3, 4? But they do this weird sort of, where'd the numbering system come from? Oh, typically when I do Roman numeral 4, I will write this, because very often with chalk, or even with a whiteboard, if you write this, and since I tend to put the bars above and below my Roman numerals, sometimes some students get that confused with a 3. Even though this is IV, since my not penmanship, my chalkmanship is not perfect, sometimes students will see this. So I will use this very often to represent quadrant 4. That way there's no confusion. It turns out in many old Roman numeral clocks in Europe, this is what they use for 4 anyway. So anyway, there it is. So at quadrant 1, 2, 3, 4. The reason they do this is, if you have an angle in standard position, and as I rotate this angle in standard position, I sweep through the various quadrants in this order. This is the first quadrant through which I sweep, and this is the second quadrant through which I'm sweeping. This is now the third quadrant, and then finally you sweep through. This is the fourth quadrant. The reason this is numbered in this counterclockwise fashion is because of trigonometry. Even way back in the very early days of basic algebra, this was a foreshadowing what was going to be happening here in trigonometry. That's why these are numbered this way. And so we can say, assuming, and this is the big deal, assuming we are in standard position, assuming we are in standard position, then an acute angle, we say acute angles, they are quadrant 1 angles. When I say a quadrant 1 angle, I mean an angle whose terminal side lies in quadrant 1. When I say a quadrant 2 angle, a quadrant 2 angle is an angle whose terminal side lies in quadrant 2. This is a quadrant 1 angle, this is a quadrant 2 angle. And then it's not very hard to see what's going on. Here's a quadrant 3 angle. And there are plenty more. If you don't like that one, there are lots of quadrant 3 angles. And then we may also have a quadrant 4 angle. And then we may also have multiple revolutions. But quadrant 1, quadrant 2, quadrant 3, quadrant 4. All right? Now, with this, we incorporate some other ideas. We can have complementary, we can have supplementary. It makes these pictures much easier to work with because we can combine the previous ideas with this standard position if that helps us to understand the problem. And we know, for example, if we have two supplementary angles, then typically what we're going to have is a quadrant 2 angle and a quadrant 1 angle. This is quadrant 2 angle. This angle, now you're saying, but Regis, this is not quadrant 1, but this angle, call this angle A and call this angle B. If I were to take angle B, this is angle B. Do we see angle B here? Angle B is not yet in standard position. If I were to take this angle and if I were to place it in standard position, it would be a quadrant 1 angle. And so any acute angle, no matter where it's located, we understand we can say that's a quadrant 1 angle because if it were put into standard position, it would then be a quadrant 1 angle. And so if I say this is angle, if this is angle C, and if I say this is angle D, angle C is a quadrant 3 angle. But look, angle D is actually a quadrant 2 angle because if I were to take this angle and put it into standard position, it would be a quadrant 3 angle. And so that language will become part of your working vocabulary. Most students pick up on this very, very naturally. It's very straightforward. One of the reasons is because it is so incredibly convenient to be able to communicate that way. And you can get your ideas expressed much more efficiently and much more accurately using this terminology and these ideas. Now, another thing we haven't really talked about, and then there's another angle type that we need to discuss, is something called coterminal. Sometimes you'll see it hyphenated. Some textbooks don't hyphenate it. Some would just say coterminal. I tend not to hyphenate it, but different textbooks do it differently. Coterminal angles. And just like supplementary angles and complementary angles, this is a pair of angles. So you need to have multiple angles for this concept to apply. This is two angles that have the same terminal side. If two angles have the same terminal side, and it is very convenient to express these pictures in standard form. So, let's pick a random angle out of the mix here. My coordinate system's kind of crooked there. That's a little better. Suppose I pick that angle at random. And let's make the arithmetic easy. Let's just make this arithmetic obvious here. Let's suppose I call this angle A. And let's suppose angle A is 100 degrees. Let's make the arithmetic really easy. Coterminal means I want another angle that has the same, if you put it in standard position, that has the same terminal side. Now, some students would want to say this. Some students would say this angle is coterminal. No, if you took this angle and put it in standard position, do we see what would happen? If this angle is put in, if this angle is put in standard position, they do not share the same terminal side. So, what we may do is something like this. Here's one way to think of coterminal angles. Multiple revolutions. One revolution and then a little bit more. So one complete revolution, right? One complete revolution would be 360 degrees. So that's my one complete revolution. And then the next 100 degrees. So that's 360 plus an extra 100, right? So if this angle is let's call this angle theta. I think we've talked about theta and alpha and gamma. So theta, the Greek letter theta, is what I'm using to represent theta is 100 degrees, all right? So if I take this same terminal side, take one complete revolution and then do 100 degrees, that would be 360 plus 100 more. So that would be 100 plus 360 is whatever that adds up to. I have 460 degrees. That's why I chose 100 to make the arithmetic easier. But if you can go one complete revolution and then an extra 100, you could just as easily, let's make a new picture just for neatness sake. This is 100 degrees. We could just as easily go 2 complete revolutions plus the 100. That would be the 100 plus 2 complete revolutions. That would be 2 times 360, which is 100 plus, what is that, 720? For a grand total of, that would be 820. So 460, 820. Let's keep track here. I'm going to take a list here of coterminal angles. One possibility is we could have 100 degrees. And then we could have, right? 100 plus 360 is 460. Right? And then we could have 820. Right? And then we could have 1, 2, 3 complete revolutions plus the 100. So we could have 3 complete revolutions. There's the 100 plus 3 revolutions. So that's 100 plus, what is that? 540. Is that right? 24. 180. Oh, sorry, not 180. That's my mistake. 360. There. 3 complete revolutions. 3 complete revolutions. 3 complete revolutions. See if I can get my arithmetic correct. 3 complete revolutions. 100 plus 1080 is 1180. These numbers get pretty big pretty fast. All right. So what do we have here? Let's take a look at what we have. From here to here, 460 minus 100, 360 degrees. If you add 360, you get this one. But this difference is also, look, if this distance is also 360, if you add 360, you get to here. If you add 360, you get to here. All right, so let's back this up. If this is 100 degrees, now think with me, if this is 100 degrees, the question is, what is that? Well, we know that, let's ignore the positive negative, we know that that number is 100, and we know the grand total must be 360. So this must be, right? If this is 100, and the grand total is 360, then this must be 260. The difference is, in this direction, that's a positive 100 degrees. This would be a negative because now we're going clockwise. And so let's think of it in a little bit different way here. To get from one to the other, you add 360, then you add 360, then you add 360. So to get from here to there, subtract 360, subtract 360, subtract 360. Do it again. Subtract 360, subtract 360. That's negative 260. And so that difference is 360 degrees. Now, what do we have? Come on, think the problem. Think the problem through. What we have, this, think of the 460. Where did that come from? That came from the measure of angle theta, which we started with 100. and we added, how many, we added 1 revolution. So that was 1 revolution times 360. This is all degrees. And then where did this come from? This was the original, and then we added 2 360 degrees is. And then we had, this came from theta, and we added 3 complete revolutions. And where did this, how many extra revolutions did we have here? This was 0 complete revolutions. And then this was -1 complete revolutions. How can we say all that? We can make this much more concise, much more precise. Because this is not very hard to see. This is pretty well done. This is still a bit of a mess. This is the way we're going to write our multiple revolution representations here. Let K equal -2, -1, 0. Let me make this a little bit bigger here. Let K -2, -1, 0, 1, 2. All right. K is any number, positive or negative, natural number counting. And so what we can have is theta plus 360 times any one of those numbers. If K is 3, we have theta plus 3 revolutions. If K is 6, we have theta plus 6 revolutions. If K is -4, theta minus 4 revolutions. And so this is the way we can represent any angle which is coterminal to theta. This is the way we represent angles coterminal to theta, and K is free to be any number, -4, -3, -2, -1, 0, 1, 2, and so on. So any integer, any whole number multiple of 360 gives a coterminal angle. So one last bit with this. Suppose we ask this now. Suppose you're asked the following. Let theta, again, let's do something easy to keep the arithmetic simple. Suppose theta is something simple like, let's say 20 degrees. Name 3 coterminal angles. Name 3 angles coterminal with theta. And all you do is you take this value, theta is given to be 20, this value, and let K. Pick any 3 you like. Any 3 you like. Any 3 of those numbers. You might as well pick the simplest ones. So we could have theta is equal to 20 plus, what could you want? You can pick K to be whatever you want. It's 360 times what K do you want to pick? Well, you probably don't want to pick 0 because then this falls out and they're not it's the same angle. So if I let K to equal 1, let's say, then this is 20 plus 360 is 380. That's my first coterminal. Call this theta number 1. Call this theta number 2. Well, what is it? It's theta plus 360 times whichever K you like best. Just pick one out of the blue sky. Just whichever one you like. Pick 2. 2 is a fine number. 2 is a wonderful number there. So this is 20 plus, what is it, 720? Whatever that adds up to, that's 740. I should put degree symbols. You should have reminded me to put degree symbols, right? Theta 3, which is 20 plus 360 times, and you can pick whichever one you want. In fact, I'm going to go wild here. I'm picking -3. I'm going off the deep end here. -3. So that's 20 plus negative. Oh golly, what's 36 times 3 is the 6 times 3 is 18, and 3 to 9, 108. and 80, right? So 3 times 360 is that. So it's 20 plus negative that. Looks like that totals up to be negative 1060. And I believe, check my arithmetic, but I believe that would be coterminal with the other angles. This is in degrees. So, given any angle theta, theta plus or minus, if you want the negatives, theta plus 360 times k, and you're free to choose k to be any of these integer numbers. And you can find as many coterminal angles as you would like.